So they figured out that there were electrons in atoms. Well, that led to more questions, and that's usually what happens with science. You find one thing, and that just opens up all sorts of other things. It's a little bit like an ant climbing up a tree, and there's a fork in the trunk, and you decide, well, am I going to go this way or this way? And the farther you go, it seems like the more options that there are. And if you come to the end of a leaf, well, you can just backtrack a little bit, and there's plenty of other things right there to investigate. So science can be pretty exciting. So if there's negative electrons, if there's negative charge in the atoms, then there's got to be something positive in there, because they knew that atoms themselves did not have electrical charges. So there's got to be something that's balancing the negative charge. So, let's trot out the theories and ideas again. Well, Thomson came up with an idea. It's now known as Thomson's plum pudding model. He proposed that those negatively charged electrons, that sentence doesn't make any sense. The negatively charged electrons were, hang on. Okay, I just wasn't able to read there for a minute. The negatively charged electrons were small particles that were held within a positively charged sphere. So this is what his model looked like. And here in the United States, we're not familiar with plum pudding. We would probably call it a blueberry muffin model. And so the blueberries in the blueberry muffin would be the electrons. And they're just sort of randomly distributed. And then the cakey muffin part is the positive charge. And that's what his idea was for the atom. You have to start somewhere, right? So he says, I think this is what's going on. And so then what do? We test the hypothesis. Well, we need to talk about radioactivity really quickly here. So radioactivity is the emission of small energetic particles from the core of certain nuclei. Only certain atoms that are unstable will give off radioactivity. And this was discovered at the end of the 19th century by Henri Becquerel and Marie Curie. And you've probably heard of Marie Curie. What was really cool about this is the discovery of radioactivity allowed scientists to probe the structure of the atom. Because now we had things that we could throw at atoms, basically, and see what happened. There are three major types of radioactive particles: alpha, beta, and gamma. And they're just named for the first three letters of the Greek alphabet. Alpha particles are positively charged, and they're the biggest. They have the highest mass of those three types of particles. So Rutherford, who had worked with Thomson, he believed in the plum pudding model. I mean, this guy is his mentor, right? And he's like, okay, well, let's test this, and we think it's true, and we're going to test it, and we're going to see if it's right. So he did an experiment, and he was trying to confirm Thomson's model. So what he did is he took these positively charged alpha particles, and he bombarded them or directed them at a very, very thin sheet of gold foil. It's really, really thin, like tissue paper. And the plum pudding model predicted that these particles would pass right through. They should just go right through the foil. But that's not what happened. Here's an illustration. So here we have the source of the alpha particles, and it makes a beam of them, a little bit like a pitching machine or the a tennis thing where it's just shooting out alpha particles. Shooting them at this gold foil, and they're expecting them to go straight through. A lot of them did. But some of them were deflected at angles, and a few of them basically bounced back. These results were very unexpected. About 1 in 20,000 bounced back. And Rutherford said this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Imagine firing a 15-inch cannonball out of a cannon at a piece of tissue paper. Nothing behind it, no magic. It hits the tissue paper, bounces back and hits you in the face. Would you be surprised? I would be shocked. You might be dead as well. But this was like, what is going on? How are these particles bouncing off the foil? They're not supposed to be able to do that. So they had to come up with a new model. This was the predicted result, that these alpha particles would miss the electrons for the most part and just go straight through. But the actual result is that some of them bounced back and some of them got bent. And this led to the development of the nuclear model, that there's a nucleus in here, that matter is not uniform. The electrons are not relatively evenly distributed throughout the atom like blueberries in a muffin, but there's something concentrated in the center of the atom. And that thing in the center has to be very, very massive for these alpha particles to bounce back. So the nuclear theory was proposed by Rutherford, 3 basic parts. Most of the atom's mass and all of its positive charge are contained in a small core that's called the nucleus. The nucleus is at the center of the atom. Most of the volume of the atom is empty space, and in that empty space we have these tiny negatively charged electrons that are doing something. They didn't know what they were doing. There are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus. Those positively charged particles are called protons. So that the atom itself is electrically neutral. If you have 5 negative electrons, there must be 5 positive protons. So this was great. It was highly successful. You know, people start testing it, and it seems to hold up. But there's one thing that didn't seem quite right. Hydrogen had 1 proton, and helium has 2 protons, but the mass of helium is 4 times larger than hydrogen. And that doesn't make sense. So basically all the mass is in the nucleus. The electrons are so small that they really just don't even matter. It's like if you were weighing a semi-truck full of oranges on a public scale, and a bird came and landed on the top of the semi. Would that throw off the weight of the truck? No, it's so small it doesn't matter. So we're just looking at the mass of the nucleus. The hydrogen had 1 proton, hydrogen atom. Helium atom has 2 protons. Protons are the same. How could the helium atom weigh 4 times more than the hydrogen atom? There must be something else in there. And so Rutherford and one of his students, see, a lot of this stuff gets passed down generationally from scientist to scientist. They demonstrated that that unaccounted for mass was due to neutrons. So in the nucleus, you have protons that are positive. You also have neutrons. They're about the same mass as a proton, but they don't have a charge. They are neutral. So protons, positive, neutrons, neutral. The mass of a neutron is similar to a proton. So we explain this discrepancy in the mass because the hydrogen atom has 1 proton and no neutrons. The helium atom has 2 protons, but it also has 2 neutrons. So it has 4 massive particles compared to hydrogen only having 1 massive particle. The nucleus is extremely dense. And extremely is an understatement. If you were able to get just the nuclei together and have it be about the size of a period on a printed page, like in your textbook, it would weigh millions of pounds, that one period, if it was just nuclei. All the density, all the mass is in the nucleus, over 99.9% of the mass. But that nucleus occupies very, very little space. So let's think about a football field. If the nucleus is the size of a green pea and you put it on the 50-yard line, the edges of the atom would extend to the goal lines. And within that large volume, a sphere, there would be a handful of electrons that are 2,000 times smaller than the green pea in the center. Most of the atom is completely empty space. So another way to think about this is the cloud analogy. So electrons are like water droplets in a cloud. They really don't have much mass, but they're dispersed over a very large volume. Clouds are mostly empty space, right? That's why, and fog is basically just clouds that are on the ground, right? You drive through the fog. Is there really any resistance? Does it damage your car just going through the fog? Not counting when you hit the pileup on 99, but just when you're driving through the fog, it doesn't do any damage. It's mostly empty space with these little tiny water droplets, right? That's the way an atom is. It's mostly empty space. There's this massive nucleus in the center, lots of empty space with little particles running around. And we'll talk more than you want to know later about what those electrons are doing. Another way to think of it. So here's like a scaffolding. If you made scaffolding the size of a football field and 100 stories high, it's mostly empty space. But if you flew over it in an airplane and looked down on it, kind of like we're looking down on here, it's going to look solid. Because we can't see through it because there's all these bars. Even though these bars are not filling up the whole structure, they're blocking our view. And so it appears solid even though it's not solid. The variation in density is too small for our eyes to see. The nucleus is dense, right around it, very not dense. Then we get the next atom, outside, not dense, inside, very dense. But those things are so close together that we can't distinguish them. So this bench top is solid, right? Actually, it's mostly empty space. So then you start to think, well, maybe some of those science fiction stories are really maybe possible. Could we transport or go through matter? Maybe we might figure that out someday. Matter's mostly empty space. Here we could stop.